I'm not a mathematician. In fact, my mathematical knowledge is extremely minute. I'm a visual artist working with ceramics, and I have a whole bunch of images for you to see. And hopefully technology is going to be kind to me and not break the presentation. So let's see. Okay, great. So for the past couple of years, I've been teaching an art and math course at the University of Washington. And the main premise of the course is iteration and mathematical thinking. So we not so much give formulas to the students, but pose them challenges and questions. So we do things in space and we do things in two-dimensionally. And we also, last year, we also taught them some basic weaving practice. And the weaving was an entryway for them to think about rules, simple rules that build up very complex systems. And you can see some student work there. In addition to my teaching job at the University of Washington, I also run an experimental ceramic studio for 3D printing with ceramics, and that is called Slip Rabbit. You can find it online with some program information, but basically we offer internships and residencies and collaborations. And some of the work that I'm going to show you today kind of grew out from Slip Rabbit, and I will finish with work that I've done for some exhibitions recently. So I have the talk sort of set up to talk to you about materiality and making, which really leads me to thinking about glitch. And I will show you why, but I will also give you a little bit of information about 3D printing, because maybe people are not as familiar with the nuts and bolts. So I'm going to let this video run so you can actually see my process. You will see a 3D printer here. And by the way, this is a project where the human hand is directly engaging with the 3D printer. So normally with 3D printing, you would be printing onto a platform. The platform is very stationary. In the case of my 3D printer, which is a PotterBot 7, the platform is moving, so the XY axes are moving constantly, and that's how they find the coordinates. And the nozzle itself, so the whole extrusion unit itself, is only rising on the Z-axis. So it's not going to move in space, rather that the platform is moving. But here the hands are actually stabilizing the form, and that's how the form is being built. The form is as a sphere, and the sphere would be, how many of you actually know about 3D printing a little bit or much or done it? Yeah, well, how easy is it to print a sphere without any support? It's not easy, right? Because it only meets the platform and in a point. So it really needs some kind of support or the hand. So this video is available on my website. You can watch this on its entirety, but you see the basic process is about layering. And the 3D printing process, you always kind of, not you, there is a software to do that for you, but it always breaks down the form to planar circumferences, basically, that will add up. And the machine will know the coordinates. So I'm going to tell you a little bit about how I got into 3D printing. It was about 7 or 8 years ago. I was working on a math collaboration with a colleague from the University of Washington, Jayadev Atreya, and we have interviewed several mathematicians at that time to talk about the creative process. And then trying to make comparisons between math creative process and art creative process. And I reached out to a couple of mathematicians, including to Henry Sagerman, who was working on this 5-cell at the time. And Henry created the 5-cell in the digital form, and then he printed it out in PLA on a very small scale. And I said, would you let me do this on large scale and with porcelain? And I prototyped, so that was the first time that I prototyped the actual parts, because I realized that in ceramics, I wouldn't ever be able to do this as a one object. I would have to break it down to its parts and then put it together and fire it together. So the object is about this size. And because ceramics basically has a live material that goes through a lot of transformation, instead of this perfect shape that Henry conceptualized, I would get these kind of crazy melty shapes that just did not want to behave, because it would have all the kind of the problems of physics, gravity, and like weight and all that. And so I think the point that I kind of want to make throughout my talk, that there is this perfect world of abstraction that sometimes you can achieve on the computer, and there is, contrary to it, there is the physical reality of the world and the materials, and sometimes they give you very interesting things. So I will show you the process of 3D printing. So basically there are 3 steps. And this is pretty much the same whether you are regardless of the material. So the first step is the form giving. It usually happens in a CAD program, but I will show you some alternatives for that. And the result of that is what's called an STL file. It's a stereolithographic file. Then that form basically needs to be translated into information that the machine can understand. And the machine code is called the G code, is created by a slicing program, although there are some ways of getting around the slicing. And then the final step is putting the G code on the machine and basically feeding the material into it, and then helping the machine to create it. So for form giving, I use Rhino 3D, Rhinoceros. And my process is extremely simple. Rhino is a very mathematical program using NURBS geometry. And what I tend to do, and the way I teach Rhino to my students, is to create basic volumes and basically stick them together. So it's no different from using building blocks. And you can see the Rhino workspace over here, and you can see some of the end results. So I'm just basically stacking and varying tori and cylinders and larger in 2 sizes, and that will give me all the shapes. I wanted to just recall this image of the printing so you can see it from close up, that if you have smaller volumes stuck onto a larger volume, and those smaller volumes are unsupported, there's usually this juicy kind of droop loop that is being created. So I discovered that by accident. And it really was just the wall was collapsing on one side, and then the next layer would just detour out to whatever it was supposed to be, and then drop down. And that's how I noticed that, oh my gosh, I can get loops. And then I really got into, using the loops, or so think about this in the computer workspace all as being like small volumes, either blocks or arches or something like that. So you don't have to draw a loop onto the cylinder. You just stick a little something volume to it, and it will give you the loop. So I started sequencing the loops and trying to see how I can get interesting forms with it. And of course, it works best on a cylinder because the radius of the cylinder is constant. So I don't have to worry about where these loops fall. It would always be at a certain distance from the center axis. And then trying to do the same on forms that had their own shape. And again, you sort of have to abstract from the digital workspace where everything looks fairly rigid. So this is a screenshot from Rhino of this object, and then the actual printed object where everything is kind of loose and droopy and juicy. And of course, this is ceramics. So once things come off of the printer, the life of the object is not yet complete. So I really get to take it apart and put it together. So this particular object was exactly like this object, except it had fallen apart because we are talking about like cream cheese consistency material that you were extruding, and then you were hoping with like about 2-3 millimeter thickness wall to build up like a 25 inch tall object. So it's so many of times these would collapse, and then I can build them together. Let me see if this moves. Nope. Oh. I don't know, maybe I'll click twice. Yes. Okay. I wanted to show you this. It's a little slow. So this object is the same file as this object. The only difference between the two is the layer height. So one thing in printing that you want to think about is that you want to squish your layer into the layer previous enough so that the materials actually stick together. If you don't do that, then you get more space. With more space, there are more accidents that can happen. So this object became this object, and then much of it fell apart, and then it was fired, and it became this object, which I like quite a lot. So I promised that I would show you some other ways of making forms. There is a way of working with meshes, which is what most of the animations that you were watching these days, CGI animations, are made of. You basically work with the surface, and it's a very intuitive process of pushing and pulling, but there is nothing exact and there's nothing measurable about it. So it might not appeal to a mathematician. There's also 3D scanning, which is something new for the studio. I got a scanner last year. You will see some of my work later where I'm actually using my hands. It's all scanned in and printed out. And then there is a parametric modeling, parametric design using basically algorithms. This is done most often by a plugin into Rhino, and that plugin is called Grasshopper. And there are other plugins that feed into Grasshopper that simulate physics and a whole bunch of things that architects might need or engineers might need. So this is a shot from a collaboration with Frank Ferris, and we are using the Fourier series to generate basically these loops that will remind you of knitting. And when they stack together in a particular way, we are getting the surfaces that look very much like purr and knit of knitting. Now, I'm showing you here my second printer. This is a much larger Italian-made wasp printer. And the really cool thing about it is that it is able to do retraction. So basically it goes around, still kind of walks around the perimeters of the object, but it can stop the flow of the material, go to somewhere else, and then restart that. So I'm able to do these little loops and then cleanly move on to the next loop. Here is an example of the exact same file printed in PLA. So the scale of this object is about 8 centimeters diameter. The scale of this object is about 50 centimeters diameter, and it's in porcelain. So very different look just because the material behaves so differently. I also wanted to show you some projects where the form did not exist and it wasn't interesting at all, because what's interesting here is there is data information that's being captured. So this is a collaboration called Listening Cups with a UX designer, Audrey Desjardins. And Audrey is interested in data that's captured in the home and how people see that. And at that time, I was very interested in how you physicalize data. How do you make it tactile? So in this project, we recorded sound in various locations. We basically took just the volume information of the sound. So not the pitch, not other things about it, just the volume. And I figured out a way to stop the printer well, actually, I noticed that when the printer stops, because it doesn't know how to stop the flow of the clay, that once it is stalling in place, it will do an extrusion in place. So the longer it stays there, the bigger the extrusion is. And I was like, that's great, right? All I need to do is to stop the printer for lengths of time, and then I'm going to have some texture. So I don't have to design the texture anymore. The data is going to give me the texture. So you will see the printer doing that. And you see that every little dot is just a moment of pause in the movement, right? So there's an extrusion happening. So later on, I used the same idea. I was like, okay, that's fun. I'm manipulating like the way the printer works, but then can I do this in some other ways? And so in this series, Pathfinder, here is the normal perimeter of the object. Then I'm using trigonometry to add for each point to create 4 alternative points. And that data will actually send the printer to one of those points. So every time I run this algorithm, I might get a completely different form, because there is no way of knowing how the data file is going to route the printer from one alternative point to another. So I always get these zigzaggy walls. Okay, so here are some finished objects. And then this last collaboration with Audrey, which we are currently working on, we are using, it's much of similar. So we are using vibration sensing in the home. And then the vibration is actually being transcribed into a differential growth, like using a differential growth algorithm into this rippling effect of the walls. And the actual finished object is going to look like this. So this has the vibration information from the home already. And the people will receive the centerpiece first. It will have the sensor, and then they will give us the data, and then we will give them back the 2 cylinders to complete the piece, which will then function as a piece of sculpture. Okay, and then you can see the printer printing that. So a couple of other mathematical projects that I wanted to touch upon very quickly. I started working on these about 4 or 5 years ago, and my interest in 3D printing wasn't so much in the object, but basically this kind of like transition or like translation from a digital algorithmic world to a physical world. And I asked some mathematicians whether they can think of some mathematical ideas where very simple rules can create complex systems. And they said, oh, you're probably talking about the elementary cellular automaton. And I was like, I have no idea what that was, but sure. And so I started looking into it, and it is how many people here know what it is? So about half. So I think it's the coolest system that there is. So imagine that you have a string of beads with white beads and black beads, and you're somehow going to read them in triplets. And then each triplet then could be translated with a key into the next generation of those beads. And then when you layer them in horizontal rows under one another, you get an entire surface of pattern. Does that make sense? A little bit, okay? So I started working with the mathematician, Sarah Billy at UW. She coded the cellular automata for me, and we talked quite a bit about what I wanted, how I wanted to use it, and this was the result. Here it is in Rhino. Again, you see that I have a big cylinder. I have those smaller volumes stuck to it, and it gives me this form. So here it is being printed. It's still like looping out, and I can play with the size of those loops, how fine they are, how dense they are, how readable they are. Sorry, but it's a little like juggly. Okay, and then here is the whole series I made about 15 different elementary cellular automata. But pretty soon I made them, and I realized that it's not random, right? It's not a chaos that I was expecting. It's not the unexpected that I was expecting. Some of them are so regular that it's almost like boring. You start generating it, and it's pretty soon it's like this the same thing repeating over and over. So I said, like, okay, let's add some extra rules to this very simple system of transcribing. So basically, I'm seeding viruses into the thing, which before the pandemic seemed like a fun idea, but we probably wouldn't want to, right, think about that anymore. But that's the regular 105 so elementary cellular automaton, and this is one with a virus that is basically just an extra rule, which said something like, if this happens 3 times, then flip the color, or something like that. So something super simple. And then this is that whole matrix plotted out here. A year later, we embarked on another project with Sarah Billy. She was interested in chip firing games and sandpile models, and I had no idea what they were. They had a math research group for that, and I sort of tagged along, thinking that I could use some of that information and translate that into ceramics. And basically, chip firing games and sandpile models, you have to imagine, again, a gridded board, and you're pouring sand into a given location. In this particular hexagonal grid, we're pouring sand into the middle, and the rules, basically, there's a very simple set of rules. Basically, most importantly, will say how many grains of sand can the cell hold. If you have 5 or more, it's going to topple, and it will spill the sand into the neighboring blocks. And that is basically the rule, and you can play it out in any type of game board. So we'll have an example of that. The color here is just the number of sand grains. So you see how, like, it goes into the center, it changes color, and then it starts spilling out. And we again ran, people who know how to program the algorithm. We ran the algorithm, and pretty soon it got so immensely complex that the computer couldn't handle the plot, and like definitely my machine was like could not handle the computation for getting this into 3-dimensional forms. We figured out a lot of interesting math just by doing that, trying to simplify the system and make it computationally less expensive. And these are some of the pieces that I would do. So for example, this one in the center has the entire matrix, the way you saw it on this colored image, which is basically saying like how many grains of sand are there in any given moment in each of the cells. But then the 4 pieces that surround it, they are the individual matrices that are containing either 1 grain of sand in the block, or 2 grains of sand, 3 grains of sand, or 4 grains of sand. Okay, so just to wrap it up, I wanted to show you how this mathematical work led me to non-mathematical work, but I wouldn't have done that work if I didn't start out with the math. So there is, you're gonna see work from a show that closed recently at the Bellevue Art Museum. It's called Object Permanence. And I'm looking at embroidery patterns now from Hungary, where I'm from. And in particular, I'm looking at cross-stitch embroidery because the cross-stitch is very much based on a matrix, very similarly to the cellular automata or the Saint-Pile models. And here are some people actually doing embroidery. So here are some patterns that you see. And I don't ever take a pattern like this and put it on my pieces. What I do instead, I will take fragments of a pattern, something like this, something like the border here, and I will put it on in the Rhino, and Rhino will allow me to apply rules of symmetry, reflection, translation, all kinds of things to it, keep layering that, and then edit those layers until I find another pattern emerging. So these are not traditional patterns. These are patterns that emerge by layering and repeating these patterns. And this is what they look like on the finished ceramics. And so for a year, I was doing them as cylinders, and I got pretty tired of how rigid they were. So again, just as a glitch, just as an accident, one time, one collapsed, and I really liked the form. So I intentionally went for collapsing them even more. And if you love ceramics, or if you've done ceramics, you might appreciate the fact that it's not only that I'm really squishing them together, I just give them that initial imbalance, then I put them in the kiln, and I pile them in the kiln, sometimes with bricks and shelves on top to give it more weight, and it will squish it. The heat will squish it. It will make the ceramic materials just soft enough. There will be a transformation happening that sometimes I don't know. The hands in here are pretty heavy, so I put them in. They keep the walls open, but they also give that weight that is necessary for them to collapse. So here are some pieces. Yeah, and this is really the very end. Here are some pieces from the show. So you see the kind of the patterns. You see how it really gets out of hand now with the accidents and stuff. And here's the show. And then I think the last image I wanted to show you, if you're interested, I wrote a book, and it's freely available online, as it is also available in a physical form. And I brought a copy here, so you're welcome to check it out. It's about everything that I said today, but it's in a more detail. And thank you. And if you have questions, let me know.